So in this session, we'll discuss the questions related to the electricity and magnetism. The first part, the potential V is applied across the capacitor. The energy stored in the capacitor is x joules. The potential difference across the capacitor is changed to 3V. The energy stored. So what is the formula which relate energy stored? We know energy stored is equals to half 1 by 2 Q into V. That's the formula. But Q can vary, V can vary. In terms of constant, we know Q is equals to CV. So in place of Q, we can write CV. So when Q is replaced by C into V, then this formula will change into half CV square. So what it shows, a relation between the voltage and the energy stored. So when we replace Q, so it will be E is equals to half CV square. So the relation between the voltage and energy, they are directly proportional with square. So if the voltage is 3V, like it become 3 times the original voltage, then what happened to energy? The energy stored will be 9 times. Why? Because it vary with a square. E is proportional to V square. So if V is triple, then E will increase by square of that number, that it will turn into 9. That's why C is the right answer. Is it clear, this question, why C is the right answer? The next question, figure 1 shows a vertical plane square coil which is having a 50 turns, which is carrying a current of 3 ampere. The length of each side is equals to 4 centimeter. Figure 2 shows the coil view from the top, and the second figure is showing a sideways. We need the force on side QS. So the force on side QS, because the QS side will be perpendicular. So angle between the coil and the magnetic field is 30, but angle between the side, like example, if we show QS and the magnetic field, so the magnetic field and QS are 90 degree to each other. So if we represent, because this is side Q and then after that there will be side S, so when we draw the magnetic field lines, the magnetic field line is perpendicular. And to find the force on the wire, what we have a formula, F is equals to BIL sine theta. That is the formula which we use to find the force on the wire which is placed in a magnetic field. So this is 0.2 Tesla multiplied by the current. How much current is passing? That is 3 ampere multiplied by length of the wire. So length of this section QNS, it is 4 centimeter, or we can say 0.04. So 0.04 multiplied by sine, and angle is 90, not 30, because we are finding the force on QNS. So on QNS, it is 90 degree to the magnetic field, but this will give us a force on one section. But how many turns are there? There are 50 turns. So the total force will be multiplied by 50. This will give us the force on one section, but there are 50 times it turn around or wrap around. So that will give us the force on the 50 sections. So as a result, when we substitute the values like 0.2 into 3 into 0.04, sine 90 is 1 multiplied by 50. So we'll get that as 1.2 newtons. Is it clear, this question? So in this question, a unit for flux linkage. What is a flux linkage? The flux linkage is N phi. That's called a flux linkage. And the unit of N is the number of the turns, and unit of flux is Weber. So what is Tesla? And we have the formula that flux is equals to B dot A. So it can be, another unit can be Tesla meter square. So Tesla is a unit for B, the flux density or strength of magnetic field. Tesla per square meter, not per square meter, it should be Tesla meter square. Weber, that's right, because n phi, n does not have any unit, n is just a number like 20 turns, 30 turns, and phi is a unit, Weber, so that is why C is a, and Weber per square meter. So Weber per square meter or Weber per meter square is actually the unit for strength of magnetic field, that is B, because this is phi is Weber, B we don't know, and area is meter square, so it will go there in division, so it will be Weber per meter square. So that is also a unit for strength of magnetic field. That's why C is the right answer. Is it clear? So the electric field strength between the two parallel plates, the strength of electric field between the two parallel plates is uniform. It does not change. Which graph shows a variation of a potential or variation of the voltage? So what happened? The voltage is defined as work done per unit charge to move the charge in electric field of, like work done on a positive charge to move in electric field of another positive. So when we have two electrodes, two plates are there, one is a positive, another one is negative. So at the positive electrode, near the positive electrode, we have to do more work done because there is a repulsion. As we move away from the positive electrode, we have to do less work done because there is less repulsion. So voltage is work done per unit charge. So near the electrode, we have to do more work done, and away from the positive electrode, the work done decreases. So it will be maximum in the beginning, and then as we move away from the positive electrode, the voltage will also decrease. So when we sketch a graph like points and draw the line, it will be a linear graph which shows a variation according to graph B. And the slope or the gradient here, because we have the formula V is equals to ED, or V divided by D is equals to E. We also say the negative gradient of this graph is equals to G. And even without like using the idea, the concept, you can also work out, as I mentioned, it's a uniform field. So if it's a uniform, E must be constant. And how E can be constant? Here E is equals to 0 because the slope, horizontal line slope is 0. Here what is happening? The slope is decreasing, so it means E is decreasing. Here slope is also decreasing. Negative and positive values are there, but slope is, in the beginning it is maximum and then it is decreasing. It means E is also decreasing. But for this one, E is constant, the slope is constant, it means the E is also constant. Is it
So, but
clear?
why is it a minus, like minus gradient?
Yeah, what is the reason minus gradient? Because when you work out the value, you will find, example, when I take y1, this will be y1 and this will be x1. When we take a gradient, we take the 2 points. One will be x1, y1, the other one will be x2, y2. So when we find the gradient here, that y2 minus y1 over x2 minus x1. So as you can see, y1 is more than y2. So the final answer will be negative. And the significance of a negative sign is the significance. So when we work out the gradient here, the gradient will not be a positive number. It will always be a negative number like -2, -5, -10. But always there will be a negative number. You got the point?
But we can just say gradient is equal to like
Okay,
electric field
okay. I
strength.
got you.
Yeah.
Means you're saying that we can say gradient is equals to E. That is
If
what you
it's gonna
mean.
be negative, like we can just find it out. Yeah.
Yeah, gradient is equals to E, but it is having a scientific meaning as well. As you can see, for positive charges, we consider their electric field is out, the direction of the electric field. Okay. And for negative charges, we consider the direction is in. Or we also say the positive charges have positive electric field and negative charges have negative electric field. What is the meaning of negative electric field? It means the direction is different, like direction is opposite. So why specifically we say that the electric field is a negative gradient? We don't say gradient, we say negative gradient is equal to the electric field strength. The reason is that because when we work out the answer, the value of the gradient will be negative, and that is multiplied by minus. So minus minus, it will, the final answer will be plus, because we are finding the electric field of a positive charge. That is why we say that electric field is equals to negative gradient. Otherwise, if I just say a electric field is equals to gradient, it means I will get a negative answer, and when I'm getting a negative answer of electric field, it means I'm talking about the negative charge, not the positive charge. Is it clear now?
Yep, I got it.
Okay, so basically the value is same as the magnitude will be same as the strength, but because there's a significance in vector quantities, as electric field is a vector quantity, so sign is having a significance. That's why we say it's a negative gradient. Otherwise, if we don't say it's a negative gradient, we just say electric field is gradient, so we'll get a negative answer. So it contradicts with the original definition, that according to original definition, the electric field of positive charge is positive and for negative one is negative. The directions are opposite. So in this question, the force on a proton at a point in electric field is 4.8 into 10 to the power minus 19 Newton. The electric field strength at this point. So how we can relate the electric field strength with a force? So we know the formula E is equals to F divided by Q. Electric field strength is force divided by charge. So electric field strength and the direction of electric field strength and the direction of the force, because of the force on a proton at a point in electric field. So the positive charges, the direction of electric field is same as the direction in which they experience the force. Like if I say there's a charge, a positive charge is placed, and this positive charge is going away. So it means what is the direction of the electric field? The direction of the electric field is out, because the definition of electric field strength, it is a force experienced by a test positive or unit positive charge, and its direction is always same as the direction of force experienced by the positive charge. So proton is positive, so it cannot be opposite direction, so it will be same direction. So either B will be answer or D. It cannot be C or A. Why? Because C and A is saying that the direction of the force and the direction of electric field is opposite. This option A and C will be valid if the charge was a negative. If there was a negative charge, then this will be valid. Otherwise, it is not valid. Because if there is a negative charge, the negative charge, what is the direction of electric field? Because electric field is always always pointing out, but because if we place a positive negative charge here, the negative charge is attracted. So the direction of the force and the direction of electric field for a negative charge is always opposite. So this will be in same direction. Now we need a force, so it will be 4.8 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19. Because the charge of electron and proton, it is fixed. The only difference is their the sign. So when we simplify 10 power minus 19, cancel 4.8 and 1.6, so this will be 3. So correct answer is 3 Newton per coulomb in the same direction as a force. Is it clear? So another question, it's a repeated question as we already discussed. The unit of the flux linkage is denoted by n phi, where n is a number of turns and phi is a flux. So Tesla is unit for B. Tesla per meter square, because we know phi is equals to BA. So flux linkage, which is n phi, so it will be nBA. N is not having any unit, it's a number. So B is Tesla and area is meter square. So it should be Tesla meter square. But this is totally wrong. Weber, again, because this Tesla meter square is also known as Weber, that's a unit for phi. And what is the unit of phi? Same will be the unit for n phi, because n is just the number of the turn, it's a number. And Weber per meter square, so Weber per meter square is actually the unit for B. So the correct answer is C for this. Then another question, there is an electrical motor. The electric motor is connected via switch to a battery. The graph is plotted to show the variation of the current with time. The switch is closed at time t. Which of the following graphs represent correctly? Basically what happened when time t, the moment we close the switch, that time there will be a drastic increase in the current. Like the current will start with the maximum value, as a circuit will have the lower resistance at that point. That's why, like example, if you try to if there is a socket and the switch is on and you try to plug in any device to a socket, it produces spark. Why? Because that moment when you try to directly connect the two, the circuit is having the least resistance, so maximum amount of charges can travel or pass. So it will start with a maximum value. So why A is wrong? Because A shows that the current remain constant. Like example, if we say 2 ampere of the current is passing, can pass through a device, the 2 ampere will continue to pass. Why B is wrong? Because it shows when we plug in the device, the current starts with a maximum value and that it decreases to zero. But if it decreases to zero, the motor will switch off. So that's why B cannot be an answer. What happened to C? C is showing the gradual increase in the current until it becomes constant, but that is wrong. Whenever we connect a circuit, in the beginning it is having the least resistance, and then with the passage of the time its resistance increases because the current produces a heating effect until the current becomes constant. That's why D is the right answer. Is it clear? Discussion? Again, this question, as we can see, this is related to electric field. Which of the following is property of a uniform electric field? A constant electric field or a uniform electric field? A field that does not change over a time. A field that acts equally in all the direction. A field that only produces a force on a moving charge. And a field that has the same strength. Because what is the meaning of a uniform electric field? The term uniform electric field, it has the same strength at all points. That this is a statement which explains the concept of uniform. Why first one is not correct? Like why first one, the field that does not change over a time. We don't bother about the time. Like example, if the field remains same, say we have a charge, a positive charge is there, and the strength of electric field example is 2 Newton per coulomb, then it become 1 Newton per coulomb, and then it become like example 0.5 Newton per coulomb. So the value of the strength is at that point, that specific point is not changing. Like example, when time is equals to 0, the strength was 2 Newton per coulomb. After 10 seconds, the strength remained 2 Newton per coulomb. So what it shows that the strength is not changing over a time, but that is not explaining the idea of a uniform. So that is why A is not the correct statement to explain the idea of a uniform. When we say B, a field that act equally in all the direction. So, like example, if I say I have a positive charge, so its field is directing, all the direction is, its field is there. So this is not correct as well. Direction, all the direction it is acting, but it is not uniform because the distance between the field lines is not same. The field that only produce a force on a moving charge, that's also wrong. Even a charge is moving or the charge is stationary, the electric field have effect both of them, have effect on both of them. That's why C is wrong. So D is the right answer. The field that is having same strength. Like example, if we say we have two electrodes or capacitor, plates of the capacitor. So if here it's 10 Newton per coulomb, at the center it will be 10 Newton per coulomb, and near the negative electrode, it will also be 10 Newton per coulomb. So throughout the strength will remain unchanged. Is it clear, discussion? Another question, a potential difference of 50 volt is applied between the two identical parallel aluminum plate. The plates are separated by distance 10 millimeter. Which combination of the potential difference and the separation would double the electric field strength? So we have the formula V is equals to ED for parallel plates, or we can say E is equals to V divided by D. So if you electric field strength is directly proportional to voltage applied, and it is inversely proportional to the distance. So we want to increase the, we want to make the electric field strength double. So when we work out the strength of the electric field from these results, like here, instead of, I'm not converting a unit, I will write in volts per millimeter. So this is 50 and divided by 10. So 50 divided by 10, originally it is 5 volts per millimeter. We want to make it double, we want to make it 10. Here what will happen? It will be 100 divided by 20. So 100 divided by 20, it will be 5 volt per millimeter. 25 divided by 20. So it will be 5 by 4 or 1.25 Newton per millimeter. 100 divided by 10. So this is 110. So it will be 10 Newton per millimeter. So, and the last one, 25 divided by 10. So that is equals to 2.5 Newton per millimeter. So when you check the options, C is the right answer, because when we change the voltage and the separation, the electric field strength is almost doubled. Is it clear? Discussion? So which of the following is not a vector quantity? Strength of electric field, it is a vector. Momentum is a vector. Magnetic flux density or strength of magnetic field, that is also vector. Potential difference is not a vector quantity. We don't specify a direction. So that's why D is the right answer. This question, we need the unit for electric field strength or value of E. So we have the formula E is equals to F divided by Q. So its unit can be Newton per coulomb, or E is equals to V divided by D. So volts per meter. So Newton meter is a unit of energy. Newton per coulomb, that's right, B is the right answer. Volt meter is not there, it is volt per, or volt per coulomb is also not the unit, so B is the right answer. In this question, two small charge objects are there. They are separated by distance d, exerting a force F on each other. The charge on each object is doubled and the distance is increased by 2. What will happen to attractive force? Like example, There were two charges which are distance d apart. A small distance d was there between them. And if the example is this charge is q1, this charge is q2, or two small charge, they did not mention identical charge, but it's okay. Then what we did, the force between them is F. So what we did, we increased double the charge and we double the distance as well. So like it become 2q here, 2q here. As I mentioned, the charge on each object is double. Like originally it was q and now it become 2q. And the distance has become 2d, double. So when we write a formula to find the force between the charges, that is given by F q1 q2 over r square, or here it will be d square. But for second case, F is equals to k 2q1 2q2 divided by 2d square. So when we simplify, it will be k, 2 multiplied by 2 is 4 q1 q2 divided by 4d square. So this 4 will cancel with 4. So what we are left with? We are left with k q1 q2 over d square. And k q1 q2 over d square is actually equal to original F. So it means the new force is same as the original force. So C will be the right answer. Is it clear? Discussion? So in this question, the graph shows how the charge stored on the capacitor varies with the potential or the voltage. So the value for capacitance and the charge stored is given at 5. What is the value for the charge stored and the capacitance? So we have the formula Q is equals to CV. So C is equals to Q divided by V. So Q is the charge, that is 20 micro coulomb, divided by the voltage, that is 5. So 20 divided by 5, that's equal to 4. So it will be 4 micro, and coulomb per volt is equals to farad. So it will be 4 microfarad. And energy stored is half Q into V. The energy, so it will be half Q is the charge, that is 20 micro. I did not convert the micro into normal number because answer is given in micro. And the voltage, it's 5. So it will be, when we simplify, this will be 10 multiplied by 5. So it will be 50 micro joules. So 50 microjoules will be the energy. That's why B is the right answer. Is it clear? This question? In this question, the diagram shows 3 bar magnets PQR being dropped simultaneously to fall through a tube at different material. One is through a cardboard, another one is copper and plastic. Because in a cardboard and plastic, there is no induced magnetism, so there is no charge produced and it will not follow any Lenz's law that it will try to oppose the change. So it will fall at a constant acceleration. Both will have constant acceleration in P and R. But what happened to Q? In Q, there's an induced magnetism, and because of this induced magnetism, this acceleration will be lower than, as when the magnet is moving towards the copper, there's a change in magnetic field, and strength of magnetic field is increasing. So there will be induced magnetism in copper, and it will try to oppose that by repelling it. So it will apply an upward force on the magnet. So the magnet will gradually, like its acceleration gradually changes. And when the magnet is passing through, the strength of a magnetic field will start to decrease. So what the induced magnetism will do, it will try to oppose the motion change. So it will try to attract. So that's why the direction from the copper is always towards upward, which is against the force of a gravity, so its acceleration will continue to decrease. So it will have a lower acceleration than P and R. P and R, there is no induced magnetism.
So B.
Yeah, so B is the right answer. That P and R, it will be simultaneous, but it will be followed by Q. Is it clear? In this question, an electric field is set up between the two parallel plates. A negatively charged oil drop is there, will experience the electrostatic force. Select a graph shows how whenever parallel plates are there, the strength of electric field and strength of force remain constant throughout, because what happens if it's a negatively charged? So at the center, if I say there's a 50 Newton attraction from the positive and 50 Newton repulsion from the negative, so 50 plus 50, that will be 100. But when it is near the positive, so there will be maybe 75 Newton attraction is there and 25 Newton repulsion, but the result will be 50. So at any point between the two plates, the strength of the electric field is constant, or the force will be constant, because we have the formula E is equals to F over Q. Q is constant, E is constant. So when we multiply, the force will also be constant. So this is always a graph for force and distance, or force and or electric field and distance, whenever we have parallel plates. Is it clear? So what is the acceleration of a proton in electric field of strength 4 into 10 to the power 4? So basically what happened, this voltage, like electrical energy supplied, is used to accelerate, or we have the formula E is equals to F divided by Q. So first we'll find the force, so E into Q will give us the force, F. And we know resultant force is equals to MA. So in place of this F, I can write MA. So I can say EQ is equals to MA. If I need acceleration, so acceleration will be equal to strength of electric field multiplied by charge divided by mass. And these are all, like, strength of electric field is given to us, that is 4 into 10 to the power 4. Q is a charge, that is 1.6 into 10 to the power minus 19. And M is the mass of a proton, that is also a constant value given at the last of the paper, that is 1.6 into 10 to the power minus 27 kilograms. So when we substitute these values, we will get the answer for this question. So B will be the answer, that is 3.8 into 10 to the power 12 meter per second square. That is the acceleration of this proton. Is it clear? A current carrying wire is placed into a magnetic field. If the magnetic force experienced by the wire balances the weight, the wire will float. The direction of a magnetic field is from west to east. For a wire to float, it is placed. So which direction? First thing, because when the wire is parallel to the magnetic field, it will not experience any force. So it should be perpendicular. So A and B cannot be an answer. That's the first thing, because if parallel, it will not experience force. Now we have like a compass, north is up, south, east, west. So wire is carrying a current uh, which is placed in a magnetic field, and what we, if the magnetic force experienced the wire balances with a weight. So which direction we should place this so that it will balance? Like example, if we are looking the ground, the weight is downward, the weight is into, because the force direction is into. What we need, because you're looking at the wire and the direction of the magnetic field strength is from west to east in this way. This is the direction of the magnetic field. So you should place the wire perpendicular. So how we should place a wire perpendicular? We should place the wire between north and south. But the second thing, how we can work out the direction? We must balance the weight. So the weight is pointing into. As you can see the wire, the weight will be into, the gravity is attracting. So we want the force to be out. We want the magnetic force to be out. So how the magnetic force can be out? When we check, if you place the wire, the current is moving. This is the direction of the magnetic field. If the current is moving from north to south, the conventional current. So we'll apply a left hand. Your first finger represent magnetic field. So your first finger should point towards east. Your second finger should point in the direction of the current, which is going downward. Where your thumb is pointing outward. So as your thumb is pointing outward, it means that this way the outward force of a magnetic field balances with the inward force of the weight. That's why C is the right answer. Is it clear? You have to apply a Fleming's left hand rule. Like,
Yes, sir.
is it clear? So apply a Fleming's left hand rule. Your first finger should point towards the right hand side. Your first finger should point towards the right hand side. Your second finger point towards the direction of the current. And thumb is pointing out or towards me. It means that the direction of the force is outward. So in this question, there are two capacitors of capacitance 1000 microfarad and 10 microfarad are charged so that they store the same amount of energy. The potential across the capacitor 1000 microfarad is V1, and for potential across the 10 microfarad is V2. What is the value of V1 and V2? So they stored same amount of energy, so we can say E1 is equals to E2. And energy stored in the capacitor is given by half CV square. So it will be C1 V1 square, and this will be half C2 V2 square. Half will cancel with half, so we can say C1 V1 square is equals to C2 V2 square, or we can say V1 over V2. V1 square over V2 square is equals to C2 over C1, or it is V1 over V2 whole square is equals to C2 divided by C1. What is this? This is the first capacitance C1 and this is the second capacitance C2. So we can say it is 10 microfarad divided by 1000 microfarad. So micro will cancel with micro, the 0 will cancel. So we are left with 1 divided by 100. So V1 over V2 whole square is equals to 1 divided by 100, and 1 divided by 100 is 0.01, or 1 into 10 to the power minus 2. So B will be the right answer. Is it clear?
Yes, sir.
So in this question, which of the following is not a unit of electric field strength? So how we can work out which is not the unit? As we know, electric field strength is equals to force divided by electric field strength is equals to force divided by charge. So it can be Newton per Coulomb, or we know electric field strength is voltage divided by distance V. So it will be volts per meter, or voltage is work done per unit charge. So if in place of voltage I write work done per unit charge, so we can say work done divided by charge into D. So it can be joules per coulomb meter, or we can say joules coulomb inverse meter inverse. Here volt per meter, and here Newton Coulomb inverse. So Newton Coulomb inverse is there, joules Coulomb inverse meter inverse is there. Then what about this one? Actually they modified, like as we know, we have the formula E is equals to F over Q. Q is the charge, so charge is equals to current multiplied by time. So E will be equal to F divided by current into time. So unit of force is Newton, unit of current is ampere, and unit of time is second. So it can be Newton, ampere inverse, second inverse. So that can be a unit, but which is not the unit, A cannot be a unit, which is joules, Coulomb inverse, joules, Coulomb, and meter inverse. Is it clear?
Yes.
So in this question, a capacitor is charged to a potential difference of 50 with a 600 microcoulomb. What would be the potential across the plate in order for a capacitor to store 50% more charge? So if you want to store 50% more charge, what is the formula? Like example, the energy stored in the capacitor, that is given by Q into B. This is the energy which the capacitor stored. And the formula which relate the charge and capacitance with voltage Q is equals to CV. So if you multiply the voltage, like the capacitance 600 multiplied by 12, 600 micro. So I did not change the micro, final answer 600 multiplied by 12. So 600 times 12, we will get 7,200 microcoulomb. So the charge which is stored right now, it is 7,200 microcoulomb. We want to store 50% extra charge. So what is the 50% of this? The 50% of this is 3,600. So we want to store 3,600 microcoulomb extra. So means what charge, total charge we want? 3,600 plus 7,200. So we want 10,800 microcoulomb. That is what we want. So when we work out from different values, C into V, capacitance does not change. So this is 600 multiplied by 600 micro farad multiplied by 3. So it will be 6 multiplied by 3, 1800 microfarad microcoulomb. When 600 microcoulomb multiplied by 9, so that will be 5,400 microcoulomb will be there. Then 600 not 1000, 600 multiplied by 18. So that will give us 600 microcoulomb multiplied by 18. So that will give us 10,800 microcoulomb. So C will be the right answer. Why 24? I did not select 24 because if I select 24, so it will be 24 multiplied by 600, which is equals to 14,400. So which is double of the total. Like it is like 100% more charge. You got the point? Because we only need 50% extra charge. So 50%, like if the total charge is 7,200 microcoulomb, so 50% extra means we need 3,600 microcoulomb extra. So the total charge on the capacitor we need 10,800. Is it clear, this question?